Hi, everybody. In this video, we're going to look at 2D motion, which generally means projectile motion, so things that are traveling through the air. So let's just imagine that we have an object and we just throw that object in the air and it comes back down. So we just tossed it up and it comes back down. So it moves sideways. You maybe toss it to, somebody 5 feet away from you or 10 feet away from you or something like that. And it makes this kind of a shape. Okay. So let's say we used some graphing software to analyze it, and we tracked its motion as it traveled along. Okay, so we just kind of kept track of it, and we kept track of the horizontal motion and the vertical motion for the object. Okay, so well, if we did that, we would get some graphs that look like this. So in this graph, keeps the blue is telling us the vertical motion, and the red is telling us the horizontal motion. So let's take a look at what this is showing. So the vertical or the horizontal motion is a linear line. So think back to this is a position versus time graph. So for horizontal motion, if we're getting a linear line, then what that tells us is a constant slope, which is therefore a constant speed. And why is this, right? Why is the constant speed? Well, there's nothing to speed it up or slow it down. So, I mean, if there is wind, let's say there was air drag or something, then we might see this line start to flatten out. But because we're going to pretend there's no air resistance, then this line, right, the object just continues to move at a constant speed sideways because there's nothing to speed that up or slow it down or make it change speed side to side at all, right? We would need something to either push it or pull it to make it speed up or slow down. Otherwise, it's going to just go at a constant speed. So let's take a look at the vertical motion. So it's curved, right? Curved means the slope is changing. Which means the speed is changing, which means we have acceleration. So let's take a look at the first half of the motion, the part on the way up, right? So as we look at the way up, right, the slope is flattening out. And the reason it's flattening out, right, so that means it's slowing down. So it's slowing down vertically. So if it's slowing down, what that tells us, right? So if we think about what's causing the slowing down, that is, of course, gravity. So gravity is always pulling this thing down. And so as a result, right, it's going to be causing acceleration vertically. It's going to cause it to slow down on the way up and speed up on the way down because we always have a downward acceleration. Gravity's always pulling things down. And so therefore, right, it slows down on the way up and speeds up on the way down, with acceleration down. So the important thing to kind of note about all of this is that we have to we have to treat horizontal motion different than vertical motion because vertical motion has acceleration versus horizontal motion does not. So we have to keep them separate. Okay. So let's take a look at what issues arise from this. So let's say that we have a cannonball fires a cannon at 60 meters per second at a 35-degree angle. So, right, that's going to be, hang on a second here, let's go with red. Right, so we fired it at 60 meters per second, and that's at a 35-degree angle. Okay, well, the problem with this 60 is that it is in both the x and y direction. And that's a problem because x direction is going to be different than the y direction, right? X direction is going to go move at a horizontal speed or a constant speed. Vertical motion is going to undergo acceleration. So what that means is we need to break it into pieces, right? So we're going to break this into a vertical piece, or sorry, a horizontal piece, and we're going to break it into a vertical piece. So we'll have our velocity in the y direction and our initial velocity in the x direction. These are both initials because um, right? Because it's the velocity that the ball is going to leave the cannon at. Now, the reason we're going to do this is because, right, this green V naught x is not going to change. Whatever that is, it's going to remain the same for the entire time this cannonball is in the air. However, as soon as this cannonball leaves, gravity is going to start decreasing the purple V naught y, right? That number is going to get smaller and smaller and smaller because it's going to slow down vertically. It's going to slow down as it goes up. And so, right, we have to split the 60 into these two parts because they're going to be, right, gravity is going to treat them differently, right? It's not going to affect the V naught y. It is going to affect, or it's not going to affect the V naught x, but it is going to affect the V naught y. So let's see here. So let's take it says find the velocity in the horizontal direction. So that's the green here. This is where trigonometry is going to come in. So we actually have a right triangle right here. So I want to find, right? So that means we're going to use some trig, some sine, cosine, and tangent. So I have the adjacent, or I'm looking for the adjacent, and I have the hypotenuse. So you go look at your trig formulas, right? We're going to be looking for the trig formula that has adjacent and a hypotenuse in it, and that's going to be cosine, right? So if we remember that cosine of theta is equal to adjacent over hypotenuse. Okay, so for us, that means that cosine of 35 degrees is equal to adjacent, which is the V naught x that we're looking for, over the hypotenuse, which is 60. So we're solving for V naught x, so we just multiply both sides by 60. And you're going to get that V naught x is equal to 60 cosine 35. Plug that into your calculator. And you get that this is equal to 49, basically 49.1. And since those units are, since this is a speed, your units are going to be meters per second. Let's take a look at the vertical now. Right, so in the vertical, we're looking for the opposite, right? We're the furthest away from the sine, from the 35. So that's going to be the sine function. Sine of theta is opposite over sorry, not over adjacent, that's tangent, over hypotenuse. So for us, that's sine of 35 degrees is equal to V naught y, initial velocity in the y direction, over 60. Same deal, multiply the 60 over. And there you go. Now you got your velocities in the x and y direction. Some of you may have noted that I wrote the wrong thing there. And of course, this is when my computer decides I can't change colors anymore. So you're just going to have to deal with a purple X. Okay, cool. On to the next problem. So this is going to be a continuation. The next question is, how long is the cannonball in the air? Let's think about this. So what dictates how long the ball is in the air is basically is going to be the vertical component, because right, when does it stop? Well, when it gets low enough that it hits the ground. That's what stops it from going any further, is that it runs vertically. It's no longer in the air, right? So how do we figure this out? We got right, this object that's flying through the air, and vertically is what affects the time. So here it starts at, um, you know, with a y of 0. Why not? Is equal to 0. We know that our acceleration is going to be equal to negative 9.8 because we have up and down motion. Our final y is, oops, our final y is also 0 because we're back on the ground again. And we know that our initial velocity in the y direction is, what did I just say? 34.4, right? We just calculated that. So we would like to know time, t. So if you take a look at all the stuff that we know, the thing that's going to be useful is the John equation. So again, like usual, please write out the the equation entirely. And then plug in all your information. So this is going to be 0. Plus, that's going to be a positive 34.4 because it's going up and down. T is what we're looking for. Negative 9.8 t squared. Now, you might be starting to get a little bit bummed out because we have a t and a t squared, but it's actually not that big of a deal. We have a 0 on this side. 34.4t minus 4.9 t squared. You can actually pull a t out, right? So we can change this to be t times by and the reason, right, so this is nice because, right, this t would, remember that in this equation would be equal to 0 when t is equal to 0, or when that is equal to 0, right? So one of those two terms need to be equal to 0. So this tells me that it's on the ground when t equals 0. Well, that's obvious because that's when I threw it. So of course it was on the ground. So so this occurs when t equals 0, which is or when 134.4 minus 9 t is equal to 0. So basically, it's 4.9 t equals 34. 4 t is equal to 7.02 seconds. So that's the one we really want, right? When does it hit the ground? How far does it go? Well, now that it's going at a constant, right? It's going at a constant speed. You could just use the John equation and put in a 0 for acceleration. We also can just say see here, x is equal to v naught x times by t, right? Because anything that's moving at a constant velocity is just velocity times time. So that's going to be, what was our 49.1 was our vertical from the other side, from the last one. 49.1 meters per second from the cosine on the other page, times by this time we just found, 7.02. Take those, multiply them together. And you get that the object's going to travel 300, the cannonball is going to travel 345 meters once you've rounded. So there you go. So it's not too bad, right? You just got to split them into their x and y pieces, and you're going to deal with the x piece and the y piece separately. Let's take a look at another example problem. So these are called the cliff jumping example problems. And a man is planning on jumping off a 20-meter high cliff into a nice lake below. How long will he be in the air, right? So much like the last time, the amount of time that he spends in the air is dependent solely on how long it takes him to fall 20 meters, right? It doesn't matter how fast you run off the cliff, right? If you run really fast or if you just kind of like fall off, you're going to be in the air for the same amount of time because you fall for the same amount of time, right? Like you can't run so fast that you spend extra time in the air. That's how it works in cartoons, but that's not how it works in real life. So so basically this 20 meters is the only thing we really need to know. Now, because he's just kind of like running off, right? The initial y velocity is equal to 0. So we don't actually need to do any of the sine and cosine that we needed to do on the last problem because, right, he only is in the air for, right, I mean, because he just runs horizontally off. So in the same way on the last one where we use the John equation, we'll just use the John equation again. Because we only have downward motion, right? At no point is this object going upwards. I'm going to pick down to be positive. So that's going to give me a positive 9.8. So if I make a list of all the things that I know, right? I know starts up here, and I'm going to call that 0 meters. He ends down here. I'm going to call that 20 meters. I know that in between the acceleration is positive 9.8, cause down is positive. And I know that v naught y is equal to 0. So I got my 20 here, 0. I have an initial vertical velocity of 0. Got my t, my 1/2, got my positive 9.8, t squared. So that leaves me basically 20 is equal to 4.9 t squared. Divide by 4.9, so 20 divided by 4.9 is going to give me 4.1 is equal to t squared. Square root that. T is equal to 2.02 seconds. Okay, not too bad, right? He needs to make sure he clears some rocks that stick 8 meters out from the base of the cliff. How fast does he have to run in order to make sure he travels 8 meters to miss the rocks? Okay, so he's going to be in the air for 2 seconds, basically, right? So in 2 seconds, he's got to make sure he goes at least 8 meters. So, I mean, roughly speaking, we can say, well, he's got to be going at least 4 meters per second, right? Because he has to sideways, right? So horizontally, he's got to be going at least 4 meters per second because he's got 2 seconds to go 8 meters. Because that's all the time he's got in the air. Mathematically, right, that works out to x is equal to the v naught x t equation. Just velocity times time is equal to your distance. So I know that he's got to go 8 meters I'm looking for his initial velocity, the speed that he has to run off the cliff, and I know that he's going to be in the air for 2.02 seconds. Okay, so do the math. Again, it's about 4-ish, right? It's going to be a little bit, yeah, 3.96 seconds. So again, basically 4, right? Nope, that's going to be meters per second, sorry. So, cool. There you go. I think we got one more here. So, lastly, we could ask other questions like how fast is he moving when he hits the water? So, probably the easiest way to do this is just with the Paul equation, because um, if we list the things we know, right? We know that the acceleration, again, we still only have downward motion, so we'd still say that the acceleration is positive 9.8. We still know that our initial vertical velocity is equal to 0 meters per second. We know that our, because right, he just runs straight off the cliff, so no vertical velocity initially. We know that our time is 2.02 seconds. And we are looking for our final velocity. So, right, you put that all together and you can see that we need to use the John equation or the Paul equation. So you probably could have used the Ringo equation as well, but Paul equation is easier. T2. So my vertical velocity is just 9.8 times 2.2. So 19.8 meters per second. So it says at what angle does it strike the water? Okay, so let's just draw a picture here. Here's the water. I got a vertical velocity of 19. I have a horizontal velocity of 3.9, well, 3.96, right? So the question is, what is the angle? Well, for that one, I'm just gonna, I have, right, my two sides. So I have the opposite and I have the adjacent. So that's actually gonna be tangent. And we haven't used that one yet. Tangent of theta is equal to opposite over adjacent. So for us, we don't know the angle, that's what we're looking for. So tangent of theta is equal to opposite, so 3.96 over adjacent, 19.8. So um, in order to do this, right, you have to untangent the tangent. So that's going to be, to do that, that's arc tangent or inverse tangent. Whatever you do to one side in algebra, you got to do to the other side. So we do that. And right, when you inverse tangent a tangent, oopsies, you just end up with theta. It undoes it. It's like dividing multiplication, two things that are multiplied. And that leaves you just inverse tangent of 3.96 divided by 19. And you can just plug that into your calculator. Inverse tangent. There we go. Okay, thanks for watching. Hope this makes sense. And we'll see you in class.